Hello friends, welcome back to the lecture series on engineering mathematics. We were solving examples on Fourier series depending upon the different range of the function, the range in which f of x is defined. For example, here in this problem, f of x is defined from minus pi to plus pi. If you try to draw diagram for the given range, this is your lower limit minus pi, this is your upper limit pi, and somewhere here is 0. So your f of x is divided in two parts. First part is from minus pi to 0. In this range your f of x is equal to 0, and second part is 0 to pi, and in this range f of x is defined as x. Since your range is minus pi to pi, we check whether this function is even function or odd function. So there are two different ways. First one is geometrical way. If you try to draw this f of x is equal to x as x varies from 0 to pi. So this is your functional curve for the range 0 to pi. F of x is equal to x. But when you consider the range 0 to minus pi, in this range your f of x is strictly equal to 0. So if you replace x by minus x, there is no direct relation. Since this curve is not symmetric about y-axis, then we cannot call it as even function. Or we can check, if you replace x by minus x, when x varies in a negative range, your function value is equal to 0. And in the positive range your function value is x. These two values are not same. Okay, means f of minus x is not equal to minus times f of x. So this implies your function is not odd. Again, this is not equal to f of x either, so it is not even. So in this case, if we consider let f of x is equal to 0 in the range minus pi to 0 and x in the range 0 to pi be neither even nor odd function. You can justify it by any method. You can give the geometric justification or this algebraic justification. If you replace x by minus x, you did not get minus f of x, that's why it is not an odd function, and it is also not equal to f of x, so it is not an even function. So from this we can identify the general formula about the Fourier series. Therefore our required Fourier series will be f of x is equal to a0 upon 2 plus summation n varies from 1 to infinity an cos n pi x upon L plus bn sin n pi x upon L. Again, if you compare the interval with the standard form, we get L is equal to pi, and when we cancel this n from numerator and denominator, we get the trigonometric function as an cos bx and bn sin an cos nx plus bn sin nx, where we need to identify values of the Fourier coefficients a0 by 2, an and bn respectively. So let's denote this by equation number 1, and therefore let's calculate the Fourier coefficients by using the formula 1 upon L integration from minus pi to pi. This is the range in which f of x is defined. We consider f of x with respect to x. Now we substitute f of x with respect to the range. Means as x varies from minus pi to 0, f of x is 0, and from 0 to pi f of x is x. Take the integration with respect to x. So since your function is 0, so its definite integral will be 0, and when you take integration here, x square by 2, substitute upper limit minus lower limit, what do we get? Pi square upon 2 pi will be pi by 2 minus lower limit will be 0. So therefore your required value for a0 is equal to pi by 2, and the first term in the Fourier series is equal to pi by 4. This is your first Fourier coefficient. Similarly, we can find value for an. Formula for an is 1 upon pi integration minus pi to pi f of x multiplied by cos nx, and then we take this integration with respect to x. So let's substitute f of x with respect to the range. In the range minus pi to pi, since f of x is 0, 0 into anything is 0, and its integration with respect to x will be 0. In the range minus pi to 0, please correct this. And in the range 0 to pi, f of x is equal to x multiplied by cos nx and integration with respect to x. So let's simplify this integration by using integration by parts rule. We have discussed this type of integral in previous example. If you have not gone through it, I request you to please go through the previous lecture. So we take first function as it is, integration of second function sin nx upon n minus derivative of first function into integration of second, that is minus cos nx upon n into n. In this range we substitute, in this integral we substitute the range of integration 0 to pi. So let's substitute upper limit minus lower limit. So in first bracket we put x is equal to pi. So it is x into sin n times pi divided by n minus minus plus. This is cos n pi upon n square. Now we substitute lower limit x is equal to 0. So since 0 into anything we get 0 plus cos 0 is 1 upon n square. So this is your upper limit minus lower limit. So if we simplify, what do we get? Here we need to substitute x is equal to pi. So 1 upon pi into pi times, what is your value for sin n pi? Since n varies from 1, 2, 3, 4, 5, 6 and 7, we are dealing with, this is your line, theta equal to 0, theta is equal to pi, 2 pi, 3 pi, 4 pi, 5 pi and so on. Means as n varies from 1 to infinity, value of sin n pi will lie along x-axis, and here sin 0 is equal to 0 as well as sin pi is equal to 0. Therefore first value in this function will be equal to 0 plus cos n pi. Since value of n varies from 1 to infinity, again we can use the same. So your angle will toggle between positive and negative side of x-axis or the both side of origin. So cos n pi will take plus 1 as well as minus 1, because cos 0 is 1. So whenever theta lies in this part, so cos 0 is equal to 1, and whenever theta lies in this part, cos pi will be minus 1, or odd multiple of pi will be minus 1. So this value will be minus 1 raised to n upon n square, where value of n varies from 1 to infinity, and this is minus 1 by n square as it is. So if you simplify this, we got the required answer as 1 upon pi. Therefore we get 1 upon pi into minus 1 raised to n minus 1 upon n square, and this is your required value for the Fourier coefficient an. Similarly, we can find value of bn. Its formula is 1 upon pi, integration is minus pi to pi. We consider f of x multiplied by sine nx, and this integration with respect to x. So we can split our f of x with respect to the range. In minus pi to 0, f of x is 0 and 0 into anything is 0. In the range 0 to pi, f of x is x followed by sine nx, and then we take its integration with respect to x. For solving this integral, we apply integration by parts rule. First function as it is into integration of second function minus derivative of first function into integration of second, where we take the range of integration from 0 to pi. Now we substitute upper limit minus lower limit. So what will be the upper limit here? Put x is equal to pi. So we got pi into cos n pi is minus 1 raised to n, because for different values of n varying from 1, 2, 3 up to infinity, cos n pi will take both plus 1 as well as minus 1 value. So depending upon n, we can find cos n pi is equal to minus 1 raised to n. So this is your first function. Then minus minus plus. This is sine n pi, and sine n pi is 0 upon n square. So you can directly take the second term in the first bracket will be 0. Now we put lower limit x equal to 0. So 0 into anything is 0 plus sine 0 is 0. If you simplify this term, we get the required value of Bn is equal to minus pi times minus 1 raised to n upon n. You can simplify this. Therefore, we get Bn is equal to minus 1 raised to n upon n, where n varies from 1 to infinity. Since all Fourier coefficients are known, therefore your required Fourier series reduces to f of x is equal to a0 upon 2, we calculated it as pi by 4, plus summation n varies from 1 to infinity. We consider value of an followed by cos ax, plus summation n varies from 1 to infinity. We take value of Bn followed by sine nx. So what was your value for an? 1 upon pi times minus 1 raised to n minus 1 upon n square, whereas this value is equal to minus 1 raised to n upon n. So you can simplify this. We take this 1 upon pi outside the sign of summation, and we can take this negative sign outside the sign of summation, and this will give us the required Fourier series for the given function f of x. I hope you have understood this.